Hi, everybody. Welcome to Best Practices in Gain Structure. We're going to talk a lot about gain structure. We're going to talk a lot about routing audio signals through the Q-SYS core, and I'm pretty excited. Achieving good gain structure is critical to getting the best audio performance out of any audio processor, out of your sound system. And there's a lot of misinformation out there about how to achieve good gain structure, and we're gonna try to combat that here this morning. So the purpose of this webinar is to start with basic terminology to ensure that there's a clear understanding of concepts that go into gain structure. We're going to move on to discuss practical applications of those concepts and the different audio routing things and tools that we've provided and have available to you in Q-SYS Designer. And then we're going to sort of talk about the whole signal flow. We're going to talk about mixers. We're going to talk about limiters. We're going to talk about our output gain structure. To do that, we need to sort of start with some definitions. So let's get into it. The first thing that we've got, I may have gone 2 slides. Yeah. The first thing that we've got to talk about is noise floor and dynamic range. Our noise floor is the baseline noise level of the electronic circuit when no signal is being processed through that circuit. Essentially, the sum of all the noise sources and unwanted signals in the system. There's another definition of noise floor that we're also going to talk about, which is sort of the ambient noise floor of a space. So if you have an open microphone and nobody's talking into it, it's still going to pick up the clinking of dishes and or the hum of an air conditioning unit. That's also a noise floor. We usually call that like an ambient noise floor as opposed to the noise floor of a particular piece of equipment. We're also going to talk about the clipping point. The clipping point is the point where an audio signal exceeds the maximum level that the system can handle. The circuitry can't reproduce that level and starts clipping the peaks of the signal down to stay within what it can process and what it can handle and what it can manage. And it will do that on both the positive and negative side of the sine wave, creates unwanted distortion, and enough clipping as you keep going up and up and up and up, your nice sine wave turns into a nice square wave. And that can damage electronics, it can damage speakers, it can damage all of those fun things. In the analog world, we use plus 24 dBu for most pro audio devices as our clipping point. Really important to note, in the digital world, that generally is 0 DBFS, and we're going to talk about the differences between that a little bit later on. Then we get into our dynamic range. The dynamic range is the range of the audio signal between the noise floor and the clipping point. The graph that you're looking at here shows the dynamic range of the CIML4 input card, which is, plus 24 dBu at the clipping point, minus 81 dBu at the noise floor, which gives you a dynamic range of over 105 dB. Pretty impressive. So now we're going to get into headroom. Headroom is something where when you have this full dynamic range, you don't want to use the whole dynamic range. You want to sort of settle in a little bit less than your clipping point so that when you have peaks and valleys and variations in the average signal, that you don't ever reach the clipping point. You give yourself, as it were, a buffer. So we need to define a buffer that allows for peaks in the signal to occur without reaching the clipping point of the system. We clearly define headroom as the difference between the average, or that average level, that level that we want to set, and the clipping point. One quick note about this, our ears aren't linear. Every time you get 10 dB louder in SPL, it's going to be perceived as twice as loud. Audio is logarithmic, it is not linear. So if we allow program peaks to be 4 times the average signal level, it means we have a headroom of 20 dB. And that 20 dB of headroom is a pretty standard thing. You see that a lot across lots of pieces of equipment. So then we get into our signal to noise ratio. Signal to noise ratio, so we talked about headroom. Headroom is kind of our signal to the clipping point. Now we need to get our signal to the noise floor. And that signal to the noise floor, that difference between those is what our signal to noise ratio is made up of. We want to ensure that the audio signal we want to hear is louder than the noise floor by enough decibels to be perceived as clean and clear to the ear, because the noise floor is always going to be there. So we want to get ourselves far enough up above the noise floor that we're going to actually have a signal that nobody's really going to hear the noise floor. Again, it takes a 10 dB increase in the SPL to be perceived as twice as loud. So if you think about that, you at least want that 10 dB. And in fact, we really want 15 dB or more. So the ratio should be as high as possible without impacting the headroom that we've previously defined. Where we start getting into trouble with these sorts of systems is when our signal to noise ratio and our headroom, when they go this way instead of being lined up. Then we have what we call nominal level. I just called it sort of the average level. And this, a lot of people call it like the sweet spot between your clipping point, your noise floor, where you have enough headroom, and your SNR's signal to noise ratio is where you want it to be. For balanced analog audio circuits, this is generally at or around +4 dBu for most professional audio circuits, for most professional audio systems. When you get into like consumer, then a lot of times you're sitting at -10. Difference between sort of unbalanced and balanced circuits in there. Our nominal level for the analog side, like I said, is we want to shoot for that +4 dBu. So then we start talking about that analog audio, and we got to get it into our core. So we've talked about some definitions. We all know what those things are. Hopefully everybody remembered that. And we need to start talking about how we get through from our analog stage to our digital stage. I always think it's really interesting that digital signal processors all have analog preamps, but most of them do, because not all signals come in exactly the same, and definitely not all of them are +4 dB nominal level. Like, the world is not perfect. As soon as you plug a microphone in, microphones can be as low as -40. They can be -20. They can be all over the place. All microphones are not created equal. And the people talking into those microphones are also not created equal. Before we convert an audio signal into the digital domain, we have to do something to get as close to our nominal level as possible. We need to, as I call it, give ourselves the best fighting chance at a good result. Once you've gone through the analog to digital converter, there's kind of no going back. So getting ourselves to that +4 dBu signal level before we even convert into the digital realm is going to make all the difference. And I can't stress this one enough. A lot of times when I get asked to help out with the system, and the first thing I do is I go and look at that analog preamp stage, and they're all over the place. And as soon as I start settling that down, it's amazing how everything through the whole DSP just starts to settle down. So after the analog preamp gets us to a more uniform nominal level, then we get into our analog to digital conversion. And that's where we start getting the signal into the Q-SYS core and can start doing some fun stuff with it. So our analog to digital conversion. We're going to talk about the Nyquist theorem. You can go Google that and get into real details. We don't need to go down the rabbit hole, but basically it's called the Nyquist theorem, or the Nyquist-Shannon sampling theorem. States that a signal must be sampled at a rate of at least twice the highest frequency present in the signal to avoid losing information and allowing the digital world to accurately reconstruct the analog signal and have it be what we would perceive as the same. The reason that we use 48 kilohertz is because our ears go up to 20 kilohertz. And again, twice that is 40, which is why, CDs were 44.1, anything over that 40 number, and our ears are not really going to perceive a massive difference. Now, some other pieces of gear might perceive a difference, and I know everybody wants 96 kilohertz sampling rates, and we'll get there, I'm sure, eventually. So the way that those sampling rates happen is over time, the digital side of the system samples the analog waveform. So how high is that? The magnitude, how high? How high is that waveform at that point in time? How high is that waveform at that point in time? And that point in time is done 48,000 times a second. So it's a lot. We're chopping this up into some pretty finely diced stuff. So that's really what we're trying to look at here when we get into the DSP. We've done our gain structure. We've gotten ourselves as close to +4. Now we've sampled it, and now we're into the digital world. So once we're in the digital world, this leads us into another value, what we call dB full scale, decibels full scale. dBu we've been talking about before this. So if I actually go back a slide, you can see that we're talking about dBu here. That's an analog measurement. And now we're talking about DBFS. So dBu and dBV are analog voltage measurements where DBFS is a digital amplitude measurement. So basically the difference between analog and digital here. dBu is referenced to 0.775 volts, dBV to 1 volt, and dBFS is actually referenced to the maximum digital signal level the device can do. So it does vary a little bit from piece of gear to piece of gear. The Q-SYS core, our maximum is 0. So used to measure amplitude levels in digital signals, whereas dBu is used to register or measure amplitude in analog signals. Hopefully that makes some sense for you guys. So then taking this, our 0 dBFS, which is our maximum digital audio level in a Q-SYS core, with our previously defined 20 dB of headroom, that gets our nominal level to minus 20 dBFS. And we're going to say minus 20 about 1 million times between now and the end of this webinar, because that's exactly what we're aiming for, right? We want to be minus 20 dBFS. That is our equivalent of that +4 dBu line level signal. All righty, moving on. Now that we're into the DSP, we're in the core. Audio is in the core. When it comes to audio signal processing, Q-SYS is what is called a floating point DSP. That means once it's digital, you can keep adding to it all you want. Is that ideal? You're gonna eventually have problems, but basically we don't put any limitations on that. Some other DSPs are fixed point, although that's becoming more and more rare, to be honest with you, where they have a fixed dynamic range for an audio signal and you really can't go outside of that. So the reason that we talk so much about the analog preamp gain and that analog to digital conversion is because once you've made it digital, you can manipulate it how you want. And I just got to be like super blunt. What you get out of it is what you put into it. If you haven't done the analog side of this, when you get to the digital side of it, you're going to struggle. But basically, we want to get to this digital point so that now that we're here, we can do whatever we want with the signal. It's kind of fun. So reaching nominal gain in the core, what you're looking at here is the mic line input block for a Q-SYS core. We want that 20 dB of headroom in the input circuit, and then we want to be targeting our minus 20 dBFS. And you'll see that peak input level there, which is measured in dBFS. So you're going to bring in your signal and you're going to basically adjust that preamp gain until you are right about at that minus 20. Are you going to be right at minus 20? Well, only if you're running a sine wave and you can get it exact. You want to get there. You want over time as you're watching it to sort of be, you'll see it doing a lot of this, but you want it to be sort of settled in around that minus 20. I always target that when I bring a signal in. This is true of all inputs. Dante inputs, USB stream inputs. We want to basically route signals through the Q-SYS core at minus 20 dBFS. As my original instructor used to say to me, you don't mix at minus 50, you mix it at unity. So moving on with microphones, they have their own noise floor based on the ambient noise in the room. We talked about that a few slides ago. AVIXA standard for speech intelligibility, and speech intelligibility means when somebody's talking, you understand the words. It doesn't sound like you're, watching a cartoon, and hearing some, announcement in the background, or you're in an airport and you hear an announcement way far away and you have no idea what's being said. Intelligibility. So the AVIXA standard says that we want at least 15 dB between the noise floor and our nominal level of our talker, for speech intelligibility. And that makes sense. Again, we're going to perceive it as basically more than twice as loud. We're going to perceive it as more than twice as loud, than the background noise, and we're going to have a good shot at understanding what's going on. When introducing microphone signals into the DSP, ambient noise levels in the room effectively become the noise floor for that signal once it's been converted into the digital domain. So if it's bad before it reaches the digital domain, it's going to be bad in the digital domain. These are big things. Like, get the gain structure right. Make sure that, especially in conference rooms, this is don't put the mic next to an air vent. Do all the things in the physical world that you need to do to get yourself to this really good starting place in the DSP. Because once it's in the DSP, there's no way to fix the signal to noise ratio. Once it's converted to ones and zeros, there's no going back. We have some tools we can throw at it. You can try to EQ out the air noise of something. You can do little tricks and tools. The AAC algorithm will do some steady state noise reduction. There's a bunch of other things that you can do in there, but now you're trying to manipulate the sound to make it better, not manipulate the sound to make it sound good. Like, you're trying to fix problems in the DSP, not actually process audio and make your system work. So give yourself a good fighting chance. So best way to check this, use the core. Have somebody talk into the microphone and then have them not talk into the microphone and have silence, and just see what the difference is between those two. Again, if our nominal level is -20 and we want at least 15 dB between the nominal level and our noise floor, that means that we want our noise floor basically below -35 DBFS. Easy peasy to check. You can check it on the line. The line input will allow you to check all those things. We give you a meter there. We give you the DBFS. So have somebody talk, you get their level. Have them not talk, you get the level. If you've got that gap and your noise floor is below -35 DBFS, you're good. If this can't be achieved, look at the physical environment. Like, go take a look at the room. Talk to people about getting acoustic treatment. Maybe talk to your performer about using a different microphone. There's all sorts of things that you can get in and do. And thank you for answering that, Steve. So we've talked about this. Yeah. So you can see that's the happy time. I always like how we have not happy, happy. All right, so now that we've got our microphone in and it sounds great, and we've got, all of our signal to noise ratio taken care of, our nominal levels where it need to be, we can start looking at processing and start looking at mixing and start looking at doing fun stuff with the signal. So one of the first things we'll talk about here is equalization. Typical equalization in a Q-SYS core: high pass filters, low pass filters, parametric EQs. These things are sort of the standardized things. You're using these things to make your signal sound good. You've got it in, you've got the right signal. Now we need to actually start making the signal sound good. High pass filter, if you just remember, if it's a high pass filter, it lets the highs pass. If it's a lows pass filter, it lets the lows pass. Usually your cutoff frequency, high pass filter, can be from 60 to 80, but you can also, if the signal is not where you need it to be, play around with that. You can take it up to 120. If you know what your subject matter is, you know what your microphones are, don't be afraid to play around with that and use that to your advantage to make it sound good. Sometimes a feed to a conferencing codec, I will raise that high pass quite a bit, whereas in the room, maybe it's not, maybe I keep it at 80 so that it sounds full and warm. Low pass, same thing. If you have a lot of, even just a weird fan noise, sometimes you can take that out of a microphone by using your low pass. People don't talk at 20K. So if you have somebody that's a wireless microphone, you can make your life a whole lot easier by putting a high pass in, lowering it to even, 15, 16 kilohertz, and just getting rid of all that extra noise and again, making your microphones sound good. Keep in mind, different microphones and different equalization can and quite possibly should be used for conferencing audio mixes and microphones versus live mixes. You also might have manufacturers that have curves for their microphones or have settings for their microphones that you want to use. A lot of times it's the same as loudspeakers, that you're going to get a, hey, come do this thing. And loudspeakers the same way. They're going to say, hey, if you do these things, it's going to get you much closer to where you want to be much more quickly. Other equalization considerations are sort of the vocal range itself. Vowels between 250 and 1K. Basically, below 250, you actually get chest resonance. Sometimes chest resonance can come up as high as 315, but chest resonance is something that if you put a lavalier microphone on somebody's chest, you actually need to think about that. Consonants are between 1,500, 5 to 6,000, and then you have sibilants, your T sounds, your Z sounds. You can play, I'm going to say play, but you can adjust your equalization to account for any number of these things. Some microphones show and reproduce sibilants better than other microphones. But if you have 4 or 5 different brands of microphones, you kind of want it all to sound the same. So you're going to have to adjust. Maybe on microphone 1, you have to take out 3.15K. And on microphone 3, you have to take out 7K. And then you sort of even out that even though they're different microphones and they have different, different elements in them and different everything in them, you can make your system and your AV system sound consistent. And that's really kind of our goal. One other thing, remember that as you remove or add frequencies, your gain is going to be affected. So if you come in and you cut, let's just say at 1K minus 30 dB, yes, you're only taking minus 30 dB at 1K, but you are taking out signal. So as you go through these, you really do need to pay attention to sort of making sure that your signal stays where your signal needs to stay to process it. Other last thing about equalization, this is just something that somebody told me a long time ago. Sometimes it's better to remove one thing than add 3 things. So think to cut first. Also think to EQ from the bottom up. And I'm, as we talk a little bit more about feedback here in the next couple of slides, I'll give a good explanation as to why. So last thing we have is feedback on microphones. So maybe we want to throw a notch feedback controller in there. One thing we recommend at Q-SYS is to throw the notch feedback controller in there, but you're not going to leave it in line, but you're going to use it as a tool. One of the hardest things to do is to find feedback frequencies in a system and notch them out without bringing in, expensive equipment like, bringing in an RTA, bringing in something that can analyze the sound for you. So it's kind of a fun little trick, as it were, to use a notch feedback controller, which is in your, your schematic library, to help you find and eliminate those feedback frequencies. So I'm just going to real quick, what is feedback? Feedback is one of those where whatever's coming out of the speaker is getting picked up in the microphone, which then gets sent right back out of the speaker, which gets picked up in the microphone. And that becomes what we call a feedback loop. And generally those feedback frequencies can be EQ'd or fixed to allow you to have a functional system. In really extreme acoustic environments, maybe this notch feedback controller stays in line. And maybe you start worrying about this a little bit more. But if your room is designed pretty well, you can actually use the feedback controller, find some of your problem frequencies in the room, and then actually just bypass the feedback controller and use your parametric EQ to take those out. So to do that, these are just the settings that you're going to do in your notch feedback controller. You're going to set fixed filter count to 0, dynamic filter count to 5, minimum dynamic frequency to 80, maximum to 20 kilohertz. So basically your whole range. And then you're going to take your system and just sort of turn it up until you hit feedback. And then what's going to really happen is the inside of your notch feedback controller is going to look something like this. And you're going to say, oh, wow, I've got a problem. Looks like 150, maybe up to 210, 215. And then, oh, I've got maybe just a hair under 600 up to, 700 or 800, somewhere in there. You can then, you can always clear these filters in the feedback controller. But what you do is you can say, oh, I've got these problem frequencies. Now I'm going to go into my parametric EQ and I'm going to remove them, and I'm going to remove them in a way that's much smoother. So a little bit less harsh, a little bit less of a situation where you've got these massive steep notches. Feedback filters are meant to be, I would say, a little brute force, because the whole idea is that they're active and live when a performance is going on. So they need to be instantaneous and dramatic. But when we're setting up a system in the beginning, we can hopefully eliminate some of that. So we can actually then create those filters, and you'll notice that in the example, we've done exactly that. We haven't done this massive minus 5,000 dB. We've sort of started with 3 or 6 or 8 dB and go kind of slow on this. Like do what's shown here, do a little amount, and then unmute and clear the dynamic filters in your feedback exterminator and see where you are and see how it sounds. One thing just to note, it is iterative, but I also tell people that you might want to wait to make microphone adjustments until after you've sort of equalized for the room. So that's all the way at the end of this presentation, but just know that you can do all of this. And then one thing about low frequencies first, you hear people say this, right? You say, hey, start low and move up. And a lot of times people don't understand why. Every low frequency has harmonics all the way up, right? Sometimes your feedback might be at 1K, but your problem might actually be at 500 hertz. So if you actually start on the bottom side, you might find yourself getting rid of less and less and less and less as you move up the frequency band or the frequency range of the system. Harmonics are a real thing. As a trumpet player, I spent a lot of time studying them and worrying about them and thinking about them. So if you start on your lowest problem frequencies first, you might find that you do a lot less as you work your way up, and your system's going to sound a lot better for it. All right, we've talked about getting the signal in, EQ, feedback for feedback reduction. Now we're going to talk about mixers. Now that we've got all our signals in, we've got a million signals coming in, we now have to mix them, and we now have a couple of options for that. We have matrix mixers. The matrix mixer is kind of the standard mixer in Q-SYS Designer. It can be operated as just a regular mixer. It can be operated as a true matrix mixer. It is, in my opinion, one of our most flexible device blocks in the system. It's just mixing and combining audio signals. You set it and forget it. It's not something you're going to spend a lot of time sort of dynamically messing with. But this is one of those that allows you to combine all the signals, get the mixes you want, and get them where you need to get them. Then we have automatic mixers. The automatic mixer is going to be the automatic mixing of audio signals. And the thing that sort of makes them what they are is that the output level stays constant regardless of how many microphones are fed into it or mixed into the output. So there's a couple of different types of automatic mixers that we're going to talk about here today. All right, our matrix mixer. You can have these big, little, however you want. I just am going to give you the label the heck out of it as you go, because you want to make sure that future you doesn't get confused. Pay attention to the options and the properties. There's a lot of unused features such as cross-point mutes that are just hidden gems in this matrix mixer. There are so many things that this thing can do. Get in there and look at those. Get into your help file and look at what those options do. Let's see. And then we say this a lot in the level 1 and the level 2 class. Make sure you set all your cross point levels. If you'll notice in the middle of this mixer block, the sort of the center of this, which is all the cross point levels, we by default have those all turned off. We want somebody to manually route it. We want somebody to go in and say, yes, I want this signal to go to this output. So as soon as you throw a matrix mixer in, and you're going to get all your inputs and you're going to get all your outputs and you're going to push your file and you go, why doesn't anything work? Well, get in there and set your cross points. All right, getting into auto mixers. I'm going to stop here. I'll read Gregory's note. I can see how adding the notch feedback filter on each microphone input would be helpful when commissioning a room, but in a live setting, would it save compute resources to just put one notch filter on the output? Yeah, absolutely. All of the processing in the Q-SYS core, that is what I call live processing. In other words, it is processing the signal in real time, and the AEC block, the notch feedback filter, and there's a couple of others. They are the things that are some of the most processor intensive things in the core. So yes, you absolutely, if you are looking at leaving the notch filter in line and working, you would definitely want to move it to the output side so that it's operating on a mix. And it doesn't necessarily need to be on the output, but maybe it's on an output of the matrix mixer. So maybe you're bringing all your microphones in and putting it there. And even if you do it that way or wire it that way in the Q-SYS core, you still could route a single microphone at a time and do exactly what we talked about while only having one block in line. So lots of flexibility there. And Gregory, that was a great question. All right, so auto mixers. And now back to our regularly scheduled. Automatic mixers have many applications, and this is one place where I really feel like if you deep dive into these automatic mixers, you're going to start using them more and more and more. It brings up a lot of concepts that we're going to talk through now, but think about things that you have that are what I call hidden feeds. Feeds that aren't actively mixed in the room, a feed to a conferencing codec, a feed to a recording, a feed to something that is not something that your operator or the people in the room know about. Automatic mixers sort of save our butts when it comes to making those sound good. Couple of the big things and concepts in automatic mixers. Max nom, or normally open microphones, number of open microphones. It's exactly what it sounds like. It's defining for the DSP the maximum number of microphone channels that can be fed to the output of the automatic mixer. We have two types of automatic mixers in Q-SYS. We have a gating and a gain sharing. We're going to talk about both of them. We're going to start here with the gating. What you're seeing here is basically an 8-channel gating mixer. And I'm just going to give a quick walkthrough. This is worth taking the time to do it, and I promise I will go fast. You have the gate over here. A gating mixer, basically when things reach a threshold, it opens a gate. It's that simple. So 5/8 signals coming in, if all 8 of them reach their threshold, we start opening gates. And that threshold is right here. The depth is when the gate is closed. How much does it duck the signal? And your hold time is exactly what that sounds like. It's how long do you hold the gate open before you close it again. And then you have this last mic on button. This last mic on button, a lot of times in a recording, a lot of times to the far end of a conference call, like the worst thing is when you lose all audio. Ooh, somebody just zipped by my room over here. When you lose your connection to the far end by muting audio or having no audio going to there, the far end feels like they've been hung up on. So this last mic on allows you to keep a little bit of sort of almost ambient noise, keeping a little bit of a noise floor going to the conferencing system. These are our channels coming in. You can see the gates open. The manual button here basically defeats the gate for that channel and says that's going to be on all the time. And then you get to this number of open mics, which is what we're really talking about here. You have a max nom, which is sort of the maximum number of mics that can be open at the same time. So this is an 8-channel gating auto mixer. And the max number of open channels right now is 8. That means that all 8 of those mics can be open at the same time. Do we want that? No. So you want to be pretty judicious with these numbers that you actually set. You want to have your max nom be 1 to 3. I think in the video for this on YouTube, Nate says you want one guy to talk, one guy to argue, and the third guy to tell everybody to shut up. 3 is a really good number for live. I've even ducked it down to 2 if I know what my application is, or I'm going to be gating ceiling microphones. If you're bringing an audio signal from an MXA 920 and another audio signal from another MXA 920, do you want both of those microphones to be open at the same time? If you set that to 2 or to 1 even, you can really control how many microphones you have open with ceiling microphones. So there's a lot you can do with this. Hopefully I went through that fast enough. So we're going to talk a little bit about now what happens to the output side of the gating mixer. So in this, you have 1 mic open, and you'll notice over here on the number of open mics, there's a gain there and an attenuation. That attenuation, as you open more and more microphones, so if you mix 2 signals together, you add 3 dB. So somewhere you got to remove that 3 dB because the whole point of our automatic mixers is the output stays static in terms of level. If the output is at 0, it needs to stay at 0. So that's what we're doing here as we're, we have 1 mic open, 1 gate is open, and there's no gain reduction that's going on. If you have 2 mics open, you now can see a minus 3 dB attenuation here. And that minus 3 dB attenuation is you now have 2 signals summed together, and you have to take out that resulting gain. And it does it on the mix of the 2. So it's actually mixes the 2 together and then lowers it down. And then you can see where if you have 4 mics open, you're down -6. So as you see more and more mics open, just from experience, as you start using gating mixers, start low and add as you need to. Start with 2, go up and down from there. That max nom is going to save your butt at some point, but make sure that you go in and set it properly. So now we're going to talk about the gain sharing version of this. So the gain sharing version of this also keeps a fixed level going out, but it does it a little bit differently. It basically says that the maximum gain is 0. And every time microphone's open, they get a share of the gain. They get a piece of that. So if 1 mic is open, it gets all of it. If 2 mics are open, they share that they each get half of the gain. So it's a little bit different way of gain sharing. It is a lot more it'll remind you a lot more if you're actually mixing these channels at an audio console, because you're going to do that. You have 1 microphone open, you bring it all the way up to 0. As soon as you have the next microphone open, you kind of duck them both down a little bit. And you have a 3rd microphone, you kind of duck them both down a little bit. So this really is how our gain sharing mixer works. Dan Dugan has a gain sharing algorithm. It's in Yamaha consoles. It's all over the place. Go Google that. It's really interesting reading. Intelligent guy who did a lot for writing some of these and coming up with some of these algorithms for automatic mixers. So let's talk through this a little bit. Same thing. We've got our setup, and we have an open indicator threshold, depth, reset gain, threshold, level, Attack, hold, and release times, those are all pretty self-explanatory. So the threshold level is the level above which to start granting a microphone a share of the gain that's there. So if this threshold level is too low, it's going to grant it to everything that comes in. You also want it to be well above your noise floor. So be really, really consistent with how you're setting that. The rest gain is the attenuation that's applied when all the mics are below the threshold. So kind of like that, how it's ducking in the gating mixer. The open threshold is the level above which to activate open LED, or basically say, we're going to give this microphone part of the gain. So turn off my pointer. So just to see this in action a little bit, you can see that one talker, all the gain is being given. You can see it's open. They've met all the basically the thresholds that are necessary. And then you have multiple talkers. And again, each mic is granted less and less of the total mixer gain. Now, this is great for 3 or 4 microphones. I mean, like, I actually, I had a friend who set up a Yamaha console, and he brought in the little Dugan auto mixer for every time he had somebody do a panel discussion with like 4 handheld microphones. And he would just hand out the microphones, and then he'd sit back and twiddle his thumbs and smile at everybody and look like, you know, and act like he was doing something great. And the automatic mixer handled it. Where this starts to get self-defeating is in large quantities of microphones. So gain sharing mixers, because it splits up the gain and gives everybody a slice of the gain. The more microphones you have, eventually it actually kind of becomes self-defeating, where there's not enough gain for to give to one signal for it to be heard. So just be aware that when you start getting into sort of the systems with 8, 12, 16, that you actually are going to get more useful auto mixing out of a gating mixer than a gain sharing mixer. All right, so we're halfway through. We've made it to basic input signals. We've talked about our automatic mixers, our matrix mixers, and I think we're going to start moving on to some other stuff, like some dynamic processing, all that other cool stuff. One thing to note, we're going to talk about user controls in a little bit, but one thing to note, you just say in this slide, there are no user controls for microphone levels. You have to probably have those. You know, if you have wireless microphones, you have to give the users a volume control. Not every performer is the same. And somewhere, somehow, somebody has to be able to turn that up and down as you change hands with that microphone. The only thing that we recommend is that you do all of this after any sort of gating or automatic mixing. Gating mixers especially are really sensitive to this, because the gating mixer is using the noise floor and how much audio there is above the noise floor to say, to make the determination of opening the gate. So if you have that as something that is dynamically changing with a volume control, you can see how the gating mixer is just not going to handle that well. All right. So now let's talk about our compressors. Our compressors, we have all kinds of dynamic processing. Our equalization we talked about earlier is definitely in the category of non-dynamic processing. So now we have some dynamic processors. Compressors are great. I am one of those people that I use them as little as possible, because they are great, but they're also not great. They really do what I call a compressor is it takes a high peak and just sort of makes it it makes a molehill out of a mountain. But it doesn't really help for quiet talkers. If you're in a really quiet situation and you're trying to get somebody louder, a compressor isn't going to get somebody louder. What it's going to do is take all your really, really loud people and bring them down to sort of a nominal level, as it were. See how I used that word nominal level in there? That was good. But you can also do AGC, and AGC gives you sort of the best of both worlds in terms of helping the soft people and bringing down the loud people, bringing up the soft people. But it's a little bit slower, less responsive than the compressor. It's trying to do a little bit more. And if they're not really set up, the noise floor and your noise floor isn't properly set, the AGC can try to increase and decrease based on the noise floor instead of the actual signal coming in. So use at your own risk. Take a few minutes and read the help file on the AGC. These can be really, really helpful, and they can be really, really detrimental. So this is one that if you see an application, use it and it's going to save you. Don't use it if you don't need to. That's how I always think of dynamic processing. And somebody's probably going to watch this and send me a note going, don't say that. So then let's talk about like where things go. A clear understanding of the use and operation of your automatic mixers will allow you to think through signal pathways like shown here, and understand why that's a bad idea. Understand why putting a gate in front of a gating mixer is going to cause problems. I also would argue putting a compressor in front of a gating mixer. What happens if you take 4 microphone signals and compress them all so they're all super close together in terms of level, and then send them into a gating mixer? Well, the gating mixer is going to probably try to open all 4 gates all the time, and you've defeated your own gating mixer. So being very aware in Q-SYS Designer of where you put things in your chain is really important. And doing it incorrectly can cause some serious problems. All right, back to our same slide again. Now we've talked about everything we've talked about up till now has been, let's just call it pre-mixer. Now we've created our mixes, and we need to start talking about the output and the output of our system. And Gregory's question was like, it was like 10 minutes too soon. When you start talking about outputs, there's a lot of things. You're going to put EQs there too. You're going to put, as was asked, you're going to put feedback exterminators in there. You're going to put peak limiters. You're going to put delays. You're going to put all the things you need to put to make the room sound good. When we get to the room equalization itself, there's 2 different things to think about. 1, what do I need to correct for the speaker? And 2, what do I need to correct for the room? Most speaker manufacturers will tell you what you need to correct for the speaker. Go get that information. Don't skip this step. You are going to struggle with EQing for the room if you don't take the 5 minutes to put in the filters that are recommended by your manufacturer. If you're using Q-SYS speakers, which we love, we call this intrinsic correction, and it's built into all of our speaker blocks. So you can just drag the speaker block, get it in there, and it's going to have all those FIR filters. Really important. Do this before you start EQing for the room. Otherwise, you're going to find yourself over EQing the room, and what you're actually chasing is the crossover point of a speaker. And having done that and gone round and round in circles and realized what a dum-dum I was being, I can just say, get the speaker processing and speaker filters in there first. And then now that you've got your speaker set up the way it needs to be set up, you can adjust for the room. The room is going to be probably your biggest battle. Conference rooms maybe not as big, but anything bigger than a conference room, anything with live reinforcement, and you really are going to need to take some time and make it sound good. Don't make it sound good for one microphone though. Like, make it sound good for the room and then make the microphone sound good, which is why I said earlier that I tend to do the room first, and then I start going through and getting my microphones EQ'd and sort of set up. So then we're going to talk about some user controls. I always call this the careful what you wish for slide. Users always want all the controls. They want to be able to walk in and make all these changes, but sometimes you don't want them to. Do they need to control a mix? Do they need to control a microphone? I tend to give the user just the things they need to control. And if it's something where I think it could damage the system, I won't give them a control. So, hey, I want the speaker volume of the entire room. Well, okay, but I'm only going to give you like 10 dB of range there, because I know that if you keep taking this up and down, you're going to blow up my speakers. So be very aware of where you give those controls, what those controls are. A good example is I actually went into a system. I live up in Seattle, so I went into somebody's company, and they were like, "Man, we really are unhappy with this background music system." And the reason they were unhappy with the background music system was because the volume control for the music was actually the volume control for the entire mix. So if they brought the music up for zone A, the wireless microphone all of a sudden was way too loud. So all I did was go into the DSP and reprogram it so that the music volume control was just the music volume control, and I didn't even give the user the output volume control. So be aware of that. Think about that deliberately. Go through that and take your time. And again, just be very, very deliberate with this. So limiting. Peak limiters or compressors. That's an argument that we could go down a rabbit hole on that we won't. A lot of times on the output side, you're going to use a peak limiter, and you want to take steps to basically protect the hardware, keep the signal within the parameters for the room, and really take the time to know that even if the user does something crazy, you've put things in place to keep the craziness from blowing up equipment. I mean, the investment here is not as much. I mean, they're going to buy a Q-SYS core. Everybody should buy Q-SYS cores. They're going to buy a Q-SYS core, and they're going to do all those things. But those speakers installed in the ceiling, as soon as you blow one of those up, right, that's where like it becomes really expensive to start fixing $100 speaker over and over and over again. So we're going to put things in our file to help us. Let's take a quick look at the peak limiter. Prevents clipping, prevents overloading of amplifiers, prevents all of those things. But one really interesting thing, the default threshold in the peak limiter is 0 dB. And you'll notice between 0 dB and 20 dB is 20 dB, which is our headroom. What happens if our signal gets all the way up to that threshold? So be aware that when you actually basically max out a peak limiter, you've literally started clipping the signal. So the default threshold, we always recommend you take it, drop it down 3 dB to -3, so that when you get all the way to plus 20, you're really at 17 and you're not clipping your system. So you can see that graphically on the output, where if you're at -3 here, you're at 21, not 24 dBu on the analog output. Just gives you headroom before clip. I've always wondered why we never went back and actually just reprogrammed the peak limiter, but that's probably things I don't need to get into. Amplifier limiting. One of the cool things about the whole Q-SYS platform and the ecosystem is that we have a lot of this built in. You don't need the peak limiter if you're using a QLAN or one of our Q-SYS network amplifiers. We actually have a couple of different types of limiting in there. We have DAC limiting, which is basically clipping the inputs, preventing clipping at the input side of the amplifier. We have going into protect due to an impedance issue or some sort of a physical issue in the field. And then we have limiting, which is based on the load type. We kind of take care of it for you. It's one of the nice things about building a system and using our amplifiers, using our cores, using the whole ecosystem is we handle and take care of all that for you. All right. We're almost there, folks. Output gain structure. So we're going to talk about this a little bit. One of the biggest mistakes that I see people make is you'll notice the analog output gain is at 0 dB all the way across. That's the default output block at the Q-SYS core. I see people just leave it there and they don't think about where the next signal goes in line and what the next piece of gear is and how we're making the conversion back to analog. But basically, this is what this is. The digital gain at the bottom is our digital gain, and the analog is, we're back to, you'll even see it says peak output level in dBu. And plus, 24 is our peak again. We're back to the analog world we started in. And you have a couple of different places where you can set this. Take the time to set this. That's all I have to say. Take the time to set this. Take the time to look at this. Take the time to understand what the input at the amplifier is if you're not using one of our networked amplifiers. So 0 dB digital gain. You'll see this max RMS output level when the analog gain equals 0. They are tied together. As you draw that analog output gain down, you'll see that max RMS output level change. That plus 21 dBu is basically to give us the plus 4 dBu nominal, plus 24 dBu max. And we're not going to, you can Google RMS and go through what that is. This is, I don't have enough time in the rest of this presentation to go into that. But take a look at that. I mean, if you're going to a consumer device, you're going into a tuner, you're going into any number of things that just can't handle plus 4 dBu, this is where you're going to make those adjustments. So the thing that we want is the biggest thing we want with output gain is we want everybody to hit clip at the same point. We want, if you clip an output that's going to a pro audio piece of gear and you clip an output that's going to a consumer audio piece of gear, we actually want that to be the same place. So this is where you're going to adjust as you make the conversion from digital back to analog. You're going to actually make that adjustment back so that, again, you're hitting clip at the same point all the way across the board. Cool thing about Q-SYS, little known fact, again, there's lots of little like, you should go look at this and play around with it. We actually can do minus 40 dBu microphone level out of a core, as long as there's no phantom power. If you feed phantom power into the output of the core, you're going to be buying a new core, which I'm okay with, but let's try not to do that. But you actually can take the analog output gain and get yourself all the way down to minus 40 dBu, which is essentially microphone level, if you have to. So if you have to feed something from a core into, say, what if you're going to another device that's a mixer or some other thing? It's really kind of nice that we give you the full breadth of the available output gain. All right. So one thing to note, go back here, when you start messing around with the output gain and you start changing your output gain levels, just know that these things are all going to mess with your signal to noise ratio. So you might have set it up all the way through the core and it's perfect and everything sounds great. And then as soon as you have to feed audio into that other device downstream, you're like, why is this so noisy? Just be aware that the analog to digital conversion and the digital to analog conversion are the places where your noise floor is going to be the most important. So pay attention to that and understand that, if you have a minus 10 dB signal or a minus 40 dB signal, your noise floor doesn't change. So you're just all of a sudden that much closer down to your noise floor. All right. We've made it through all the death by PowerPoint slides. Just some things to talk about in terms of some important concepts we've talked about through this whole thing. Make sure you're adjusting your analog gain at that analog preamp before the signal is converted to digital. All inputs receive the same treatment. Microphone equalization, we talked about how to do that, talked about how to use the notch feedback controller to your best advantage. Microphone dynamics, compressors, automatic gain control, getting consistent, levels from wider range of talkers. These are the equalization, dynamics, auto mixing. These are all things that we could probably talk about for days and days and days and days. And if Steve actually unmuted himself and turned on his camera, he and I could go back and forth and not agree for at least 2 hours on anything. These are all very subjective things. Find what works for you. Find what gives really good, consistent results to your end users. And within companies, so say you work for an integration firm, come up with some standards amongst yourselves too. Like, we're always going to do it this way to get consistency so that when our service tech shows up, he's looking at consistent things. Very, very important to get that consistency and get those end results. Fewest user gain controls to get the job done. We've talked about that. Auto mixing, don't put level controls or gating or those types of things ahead of auto mixers. Knowing when to go from gain sharing to gating, the more microphones, the more you want to tend towards the gating auto mixer situation. Output limiting, we do it great. I love that. Q-SYS amplifier limiting applies automatically. Peak limiter can help you out when you're not using a Q-SYS network amplifier. And then again, just being very aware of where you're going to go to that analog stage at the end where you're going from digital back to analog again. And so making sure that you're taking the time to set the analog output of your core, just like you set the analog input of your core. All right, we are done. We are done on time. I feel like I should get a little trophy or statue for that because that's a first for me.
It's in the
Um,
mail.
it's in the, yeah, I'm sure I'll get just a big star sticker. And if there's any questions or anything that anybody wants to ask, we have a few minutes and we can stick around. Um, using project, okay, I'll read out loud. We have a Bluetooth wall plate that we use in projects, and they have a really hot output feeding to an input on the core, and it will clip when the preamp is all the way down. Any suggestions on how to attain the minus 20 dB level on a really hot input? That's really interesting. And there's no adjustment in the Bluetooth wall plate. That's concerning. Most of the Bluetooth plates that I've used, you actually can go in and set them up and actually set what the level is coming in or out of them. If they are clipping when the preamp, analog preamp is all the way down, um, I hate to say don't use that wall plate, but man, I'd really be thinking to find another wall plate. You can use inline pads, but if it's a Bluetooth signal and it's sending, is the output of the Bluetooth signal analog audio? In which,
That was going to be my question. Is this an
yeah,
analog thing or a digital thing? Because, I mean, I've used a ton of the Undy 6IO BTs, which are the Ateratech Bluetooth
which you
plates.
have which you can actually go in and
Yeah,
configure
yeah, because those are coming in Dante or AES 67.
analog output. Okay, so if you really, really have to, you can put inline 20 dB pads. It's not great. It's not ideal. I don't really want to do it because that's just another thing in the chain that can fail. But I would really, really look at what you're doing and what you're using for your wall plate. There's lots of good Bluetooth wall plates that are Dante, and AES 67. We sell one, but there's a lot out there on the market that aren't going to give you that kind of trouble.
Yeah, so Chris just asked this question. This is exactly what I was about to cover as sort of part of our wrap up. Within about a week or so, the marketing department will package all this up. You'll get a recording of this along with the slide deck. That holds true with any of our deep dive webinars. So long as you register for it, you don't even necessarily have to attend, but so long as you register for it, you will receive that wrap up email with the link and any of the materials that we have. Also, as a build on this one, I know we had some questions regarding some of the other processing blocks. So there is another deep dive webinar that's called dynamic audio processing that goes into things like compressors and limiters and gates and automatic gain control and noise compensation and all of that. So if you do have other questions about that kind of stuff, there is a whole other webinar where we start to really jump into that. Same thing with AEC. That's its own webinar because that one I guarantee you, Angela, will not get through in an hour because there is a lot to that one.
I have yet to make it through that in less than like 90 minutes. Come on.
Yeah, yeah, that is a deep dive. It's the deepest of the dives.
Fist of the dives. All
Anything
right.
else?
If there's
Awesome.
no questions, it means I did my job.
You did such a great job. Either everyone is just stunned or they have all the information they're ever going to need when it comes to gain structure.
Or they hung up 15 minutes ago.
That too. All right. Well, we appreciate everybody's time. Thanks for coming out. And we will see you guys on the next one.
Thanks so
Have a
much,
great
everyone.
week.